G'day, my name's Liam, and my final year research project was on investigating the forestry / ignition capabilities of a plastic sphere dispenser ignition bulb. So I'll start with a bit of background. Why do we want to burn forest slash? Burning slash will reduce the risk of a forest fire starting on a cutover and ending up in the forest, and it reduces the risk of slash mobilizing and ending up down the hill somewhere it shouldn't. It also removes the need for slash management post-harvest, makes it easier for planters for replanting, and creates a nutrient-rich layer of ash on top of the soil. As well as this, we're seeing an increase in mechanized harvesting, which means there is being more and more slash left on cutovers, which is thus increasing these risks and hassles that I just mentioned. So burning slash is nothing new. It's been done for years before, and it's still sometimes done now. So typically this has been done with a ground crew with a drip torch or with a helicopter with a drip torch. However, both of these methods are costly and dangerous. A delayed aerial ignition device or a plastic sphere dispenser has been used in the USA as a means of wildfire control in the past, and these have been attached to helicopters. However, more recently, these PSDs have been developed and can now be attached to a drone, which means there's potential for these new drones to be used in igniting our cutovers in a safer, cheaper, and more effective way. So my research question was, is a plastic ignition sphere that is used by a PSD ignition system able to successfully ignite forestry / post-harvest, and what are the factors that contribute to the successful ignition? And so this involves the objectives of determining the properties of an ignition sphere, determining if an ignition sphere can ignite forest slash, determining how moisture content and slash changes over time, and whether this is an important influence in the capability of the ignition spheres, and then identifying what other factors are likely to influence the ignition sphere's capability. So onto the ignition sphere. So in this investigation, I used SEI Industries ignition spheres, which I've got here. And so these have a hard plastic shell which contain 4.8 grams of powdered potassium permanganate inside. What you do is you then inject ethylene glycol into these balls, and it causes an exothermic reaction which causes the flame. In my research, I found that you're meant to use 1 ml of glycol when injecting. However, this did not work for me, and I instead found that using 0.25 ml of ethylene glycol is what causes a successful ignition of these spheres. So I also found that within 15 seconds of injecting the glycol, the ball would be smoking, and within 30 seconds of injection, the ball is flaming. This flame would then last for approximately 150 seconds or 2.5 minutes. I also used an infrared thermometer to measure the temperature of the balls. And so what I found is that in the first minute of ignition, the ball would reach an average temperature of about 270 degrees Celsius with a maximum temperature of about 320 degrees Celsius. Over the second and third minute, this temperature then decreased to an average of about 180 degrees Celsius before it extinguished. So in order to test these balls on slash, I needed to collect some slash, and Port Blakely were kind enough to grant me access into Geraldine Forest on the condition that I don't light any fires in their forest. And so I was able to find 6 suitable cutovers in Geraldine Forest, and these had the age 0 to 3 months, 0 to 5 months, 5 to 6 months, 6 to 8 months, 10 to 12 months, and 14 to 17 months since harvest. What I then did is visited each of those sites and collected 8 samples of slash from each. And so to do this, as you can see in the top right photo, I'd take a 1 meter squared area and put that on the cutover. I then collected a representative sample of slash from within that 1 meter squared and filled up 1 60-litre rubbish bag. A representative sample means that I collected fine fuels, medium fuels, and coarse fuels as was represented within that 1 meter squared. And I only used 1 60-litre bag per plot, because otherwise I could have had 20 bags per plot, which would have been not possible or not handy. And so, as you would all know, we had a very wet winter this year, and this meant that I had some troubles with collecting slash. And so when I was finally able to collect slash, it had been raining, and so the slash was all rain wet. To mitigate this, I reconstructed the samples off-site, and then I left them sitting for 7 days in order to dry off the rain wet, but not change their true moisture content. And so the bottom two photos show my sample reconstruction. And as you can see on the right, again, I used a 1 meter squared area and tried to reconstruct samples that are similar as possible to on-site. So after 7 days of sitting, I was about to conduct the test burns. However, just before I did this, I collected some more samples from each of the reconstructed piles. And then I took these samples back to the university and put them in an oven at 70 degrees Celsius in order to work out the moisture content. And this was an average moisture content, so it had fine, medium, and coarse materials all together, and it was an average of them. I did this because separating out these different size materials would have been very time consuming and not necessary. As we can see in the graph on the right, these are the moisture content results. So as the age since harvest increases, we see a decrease in the moisture content of the samples. And at about 6 to 8 months, we have the minimum moisture content. After this, we see a slight increase in the moisture content. And this is likely due to the slash starting to rot, which increases moisture content. So onto the test burns. So to do this, I ignited samples one at a time, and I recorded the time taken to ignite the needles, twigs, medium fuels, and coarse fuels. You'll notice that I've split fine fuels into needles and twigs. This is because a medium fuel is classed as 3 to 7 centimeters in diameter, and this meant that I can't capture the difference between a needle and a twig in the fine fuels, medium fuels. I then also observed what factors may have contributed to success or non-success of the burns, and then I observed the overall burn area using before and after photos, like the example at the bottom of the screen. And so these are the results. So in both graphs, blue shows needles, orange shows twigs, grey shows medium fuels, and yellow shows coarse fuels. And so on the left, we've got the number of successful sample ignitions. And so as the age of the slash increases, we see more and more success at igniting these different types of slash. And at age 5 to 6 and 6 to 8 months, we have 100% success at igniting needles and twigs. After this, we then see a bit of a decrease in the success. In the graph on the right, it shows the time taken to ignite these different fuel types. And so similarly, we have, as the age increases, we have faster ignition times, and at 5 to 6 and 6 to 8 months, we have the fastest ignition times. After this, the ignition time then increases slightly. So I was then able to answer all my questions from the research I'd done. So yes, the ignition spheres are successful at igniting forest slash. The best ignitions were observed in slashes 5 to 6 months old. And this is because there was 100% success at igniting the slash, and that happened in the fastest time possible. Yes, the moisture content of slash does change over time, and this did appear to influence the ignitability of the slash. And finally, needles were seen to be the most important factor to consider for successful ignition. So without being able to ignite needles, nothing else is able to be ignited. And finally, I've got further details in my report I've written, so please get in contact if you would like to read it. Thanks.